And today we are going to talk about the category cabling. Now, you might want to pay attention to this particular class because this is something this knowledge that you have, you are going to use that in the field, whether you're working within that or whether you're just basically living in 21st century. You will come across tasks that involve this sort of information and knowledge. Okay. All right. So before we start, how many labs are there left? How many labs are there left? Let's check. I'm going to switch to this thing here. How many labs? Let's see. And grades. Hold on. I'm just going to manage grades. All right. So we are at the patch panel right now, and then UTP, coaxial cable, and optical fiber. All right. So we're going to have an open lab. Let's see where we have the open lab here. So yeah, we just have 2 labs left. Now, did I designate 1 session or did I designate 2 sessions for that here? Course outline, let's just take a quick look. Labs. Yeah, that's going to be week 13 and 14, which means that the coaxial cable, which is a very simple lab, we're just going to put an ending, terminate the coaxial cable and get evaluated on that. So that should take you about 5 minutes doing the lab itself. However, there is going to be a somewhat extensive information session, and I have that recorded, so I'm going to ask you to watch that, and I really, really encourage you to watch that. So coaxial cable here. And also we are going to do the optical fiber splice. We are going to perform a fusion splice, which means it's a supervised lab. What do I mean by that? Every single person that is going to perform that splice is going to be supervised directly, because there are certain safety measures that have to be taken when dealing with the optical fiber. And if you have never done any of that, it is an extremely good idea for you to be supervised, and you will know why. All right. Yeah. Let me just go back to the original queue here. All right. 5. Category cabling. All right. Category cabling. Now, this looks like category cabling, because the picture I took was from one of the huge facilities that we have in our town. It could be, you know, if somebody showed me this picture and told me that it was a category cabling, I could have mistaken this thing for Cat 6A, all right, because that's basically that thickness of the wire. It's just like a coaxial cable. I just took the picture of that because it's nice and colorful, and it shows some well done cable management when it comes to that, and you know, it's a nice colorful picture. Right now, right off the bat, can you spot any cabling faults here? That's if it were category cabling. All right. Anybody, any idea so far? Anybody who has done any of that? Maybe, you know, sometimes we get people who have done some of this work already in the field, and if you don't know, don't worry, I will tell you. Okay. So what is the problem with that? We can see here that there are some sort of zip ties being used to for binding of those cables. If that were category 6A, that would be a big, huge no-no. All right. Simply because when we squeeze or alter any, even in the slightest way, well, in the slightest way, it's an arbitrary term, but if we alter any structural integrity of the cable, and by squeezing it too much, also that counts, we are actually altering the specifications of the cable. If this was category 6 or category or even 5E, which is the most forgiving out of the what's on the market right now, it's being used, but still I wouldn't use the zip ties on those. What we should use is the Velcro tape in order to bundle those cables. So that's what's wrong with this picture right here, if this were a Cat 6A cabling. All right. Now, what I'm showing is here. This is quite often you'll be able to buy just those big rolls of Velcro tape, and you'll just cut them to length and use them to bind the bundles of the category cabling. Right, and it says soft side in. The Velcro has that soft side, and it has those plastic sort of like hooks, kind of a little tiny hooks there. So it's not going to make that much a huge difference if you use it the other way, but anything that you can make the category cable, the more comfortable you make it, the better for you, right? And for the cabling. All right, now this Velcro comes in many different shapes and forms, sometimes wider, sometimes narrower. Now this is basically how we do this. Now, I know you won't be able to see this on this video presentation here because of the bandwidth of the zoom bandwidth. It kind of narrows it down, so you're going to see a little bit blurry picture. However, when you download this, you probably already have the posted lecture notes. You'll be able to see it more clearly. What's wrong with this picture right here? Remember I said soft side in? This is not a soft side in. It's the other way. So right here, this is wrong. The soft side on the, what do they say here? The soft side of the tape is on the outside of the bind, right? So it should be soft side in. All right, now, let's say, just follow me on this one here, okay? Let's say this is a single conductor. Okay, it goes somewhere, forever somewhere. It's a part of the circuit. Right? It goes somewhere there. It's connected to some kind of a circuit, and let's say it continues the other way. Also, it's basically part of a complete circuit. Current flows through it. All right. And the current, let's assume the conventional current flow, which means in the conventional current flow, we assume that the current flows from the positive or the more positive side of whatever device to the more negative side of the device, except if it's a source. Then of course, if it's a power source, then the conventional current flows from the negative to the positive, because if you just draw that, if you draw the circuit, let's say here, all right, so of course this is a positive side, this is a negative side of the DC power source, and conventional current flow, the current I would flow this way. So this would be the more positive side of the resistor, this would be the more negative side of the resistor. Yeah. So the current would flow through that. It's a voltage drop. Now, when you just follow the current here, if when the current just flows through the source, so in the source, the current flows from negative to positive. As opposed to the electron flow, then we would consider the electron flows. The electrons flow from the negative to the positive. So there are two ways of calculating circuits: conventional current flow and the electron flow. Now, it doesn't matter which way you assume in order to calculate your circuit, as long as you stick with one method from the beginning to the end, then your calculations are going to be good. Right? Now, so let's assume that this is a conventional current flow, and the current flows from the positive side to the negative side of this, whatever it is, a conductor. Okay? Now, when that happens, electromagnetic field forms around this conductor, and it just basically makes circles around it. Okay? The direction of the electromagnetic field is just like if you were using a corkscrew. If there are any wine drinkers in the crowd, you turn the corkscrew to the right. All right, you just turn it this way, here, like that here. So then you would the screw part of the corkscrew would turn righty-tighty clockwise, and the corkscrew would move with the direction of the current, and basically, so that's how the electromagnetic field. So just so you know, right? So let's get rid of that corkscrew right here. Now, let's say we are going to introduce another conductor right beside it, right along its way. So parallel to it, close enough. And this conductor is not connected to a source. Let's say it is connected to just nothing else but a load. So it could be connected to a resistor, for example. So on its own, nothing should be happening in that circuit because there is no power source, right? Now, if you bring that conductor in close proximity to the conductor that is actually active, the current flows through it, in a way that the electromagnetic field is going to affect that other conductor, we are going to induce a current flow in the other conductor. Right? So that's important concept that we gotta remember, right? So the current flows through the other conductor by the means of induction. That's how transformers work. Sometimes we want this thing to happen in the transformers, yes, we do, and sometimes it kind of works against us, all right? And when it comes to telecommunications and using data or telephone or any kind of signal wires, this is not such a good phenomenon for us to be happy about, right? So now the current is going to flow in the same way, right? If the conductor is placed in cross proximity in a way that the electromagnetic field is going to affect that other conductor, all right? So in telecommunications, we call this thing a crosstalk, right? What does it mean? What's a crosstalk? In electronics, crosstalk is a phenomenon by which a signal transmitted on one circuit or channel of a transmission system creates an undesired effect in another circuit or a channel. So basically, it's a form of interference, right? And in telecommunications, we call it crosstalk. Right? Crosstalk is usually caused by undesired capacitive, inductive, or conductive coupling from one circuit or channel to another. So it's just another way of putting it. All right. In structured cabling, electromagnetic interference from one pair to another. Because remember, when it comes to telecommunications per se, this type of telecommunications that we're studying right now, we are not talking about how many wires are you going to run from one point to another. In telecommunications, it just so happens that we are, for the convenience of things, we're calling it pairs, because usually we're using pairs. One circuit is usually one pair, or it's just used to be that way, or one transmission line would be one pair with the telephone, so it kind of stayed that way. So we're talking about pairs. All right. Crosstalk in analog systems. The crosstalk affects analog systems slightly different in a different way that it affects the digital transmissions. Okay, so let's say we have a very pleasant telephone conversation between two wonderful people. All right. Now, let's just imagine that the signal passes through a trunk, and a trunk is, in telecommunications, a trunk is a bundle of cables. It's a cable that contains many different pairs, kind of condensed into one sort of physical cable, right? So that's a trunk. All right, so let's just say there's another conversation that takes place between two other wonderful people, and it's just as pleasant. And some of the wires are passing at some point. Those lines or those pairs are kind of in close proximity to another. Right? What would normally happen by the means of induction, we would have one line could be affected by the other. And we're talking about something that we can call a bleed through. The signal can bleed it's bleeding from one pair to another. Right. So now it's not as much of a problem with the telephone conversations these days. This is right now we're 2021. Now, in the earlier days, like a few years ago, maybe 10, 20, 30 years ago, there was a problem actually, and sometimes, actually quite often, once in a while you will be able to, when they were talking on the phone, you will be able to hear somebody else's conversation on the other line, right? And sometimes you actually will be able to talk to the other. Sometimes you will be able to just hear, and when the crosstalk was bad enough, sometimes you would actually be able to communicate with the other conversation when it takes place. Right. So that's a crosstalk. Okay. Now, just because we don't hear that when we are using our telephones these days, doesn't mean that the crosstalk doesn't exist. Right? Crosstalk Digital. Now, there is a video that once you download this presentation here, click on this link, and this is there's a demonstration of what happens when crosstalk happens in digital circuitry. And I'm going to explain, oops, not yet. I'm going to explain this to you. Now, when it comes to analog systems, a crosstalk can be annoying. Right? You will still be able to hear the conversation. You should be able to carry the conversation with another person. You would still be able to hear the transmission words like music, or maybe even if there was video, like a television transmission, you would still be able to see the transmission or receive the transmission. However, if there was a crosstalk, if it's a conversation, you would hear some interference, some noises, or maybe some other conversation taking place. If it were a television transmission, maybe you would see some other channel cutting in a little bit, bleeding through, and so you would still be able to see whether you're supposed to see the transmission, the original transmission, but it would be annoying because the other channel would kind of interfere with the original channel, right? To the point that sometimes if the other channel is too strong, it would just take over and the original channel would disappear. So, but for the most part, it would be annoying. Now, when it comes to digital crosstalk, when we have two transmission lines that are close proximity, if one channel bleeds through another, just think about how the digital transmission takes place. Well, for the most part, it's like a serial communication, not parallel. Right? So which means what that means is that at some point you're going to send a bunch of ones and zeros in certain timing intervals, and those ones and zeros are going to travel through that line, and they're going to be received by the receiver, and usually it would be that received transmission would be timed. So first you would send, most of the time you're going to send some sort of a beginning of a transmission, and when the receiver receives that, it says, okay, that's my time 0 right now. Excuse me, I need some water. So from that time of reference, that receiver is going to count the time, and it's going to be timed pulses, and it's going to interpret when do I receive 1, when do I receive 0, how fast are they coming, and it's going to be able to bundle those data packets and make sense out of that. Right? Now, when it comes, that's how the receiver, the digital transmission, for the most part, in a simplified kind of way, takes place. Now, when some other transmission cuts in, the receiver is going to receive those ones and zeros that were supposed to be, but there are going to be some other ones and zeros cutting in. So then it's going to be to the point that the receiver is not going to be able to know what the transmission is, right? So when that happens, there is not going to be an interference, like annoying interference. You're going to have that receiver saying, okay, I shut down, right? There's no, no, I can't, I don't know what they're saying, what this transmitter is saying. I don't understand this signal, I'm just going to shut down. So the difference between the analog systems, crosstalk or interference, is that in analog systems it can be annoying, but when it comes to digital systems, the transmission is just going to cut off. Right? And this link that I'm showing you here, that well, you'll be able to click and play that. It's a 3-minute video, right? So not much time of your life. It's just a demonstration of what happens. It's basically what I just told you. Now, this is in this video, it's a little bit more exaggerated example, because this person, there is just what happens if you place one data cable beside the other, but then you're going to see a bunch of LAN rooms that you have bundles of cables going beside each other. So this is an exaggerated example here, but it still can happen. All right. So watch that, and you will know what I mean. Right? Now we're going to move on to something that's called a UTP. UTP. What does that stand for? It stands for unshielded twisted pair. All right. There you go. That's the data cable that we are pretty much using through the most of our course during our labs. The idea of twisting a pair goes back pretty much to the time when the telephone was invented by Mr. Alexander Graham Bell, and he actually was also the one who invented the concept of using a twisted pair. Just think about it. When you have two wires that are straight beside each other, transmitting, and the other one is beside it, so the other pair could be affected by the first pair. If they're straight enough, nothing, there's no any alterations of how they physically run. They run right beside each other. So if there's a longer distance of those wires being straight beside each other, there is a better of a chance of the other wire being affected by the first one. Now, when you twist the pair, just twist the pair, the magnetic field that is along the first pair is not as strong, not as consistent. Right? So it's dispersed, electromagnetic field. So there's a less of a chance of it affecting another pair. Now, when you have another pair beside it, and it's also twisted, you don't know if it's, well, there's a very slight chance of them being put right so the twists align. Plus, when you have different pairs, they are going to, if you have one pair being twisted with one twist that's of a certain speed, or it's going to be so tight. Now, if there's another twist that's going to be not as tight, maybe the twist is going to be slightly different, not as dense or not as rare. So the twists are different, then there's even less of a chance for the crosstalk to happen. So that's why the twisted pair, that's why we use twisted pair to transmit data signals. And why do we twist the pairs? Is to avoid crosstalk. All right. So that's when we are talking about. I think you see those. There's green pair here and there's brown pair, and you can tell that the pairs are twisted slightly in a slightly different way. All right. So that's why we're using twisted pair. The purpose of the twist is to eliminate crosstalk between pairs. It worked quite well when it came to telephone conversations, and when it comes to data transmissions, it's crucial that you use twisted pair. Now, as a side note, I'm going to tell you, now you have a twist. So think about that. A twist is just a little bit of a winding on the cables, on the pairs, on the conductors. So in a way, you could consider it's going to carry some of the characteristics of a coil, right, or inductor. So now think about that. Now, sometimes we want a twisted pair in telecommunications, and sometimes we don't want a twisted pair in telecommunications. When it comes to transmitting data, yes, we most definitely want to have twisted pair. But sometimes when it comes to, for example, let's say alarm systems, door contacts, or contacts, well, how does it work? There's a contact. There is a zone of alarm system or a circuit, and it does have a wire running from that zone, and it's terminated on the other side in just something that's called a reed switch for the most part, and there's a magnet here. So this wired part is going to be part of the door frame, and this magnet is going to be mounted on a door actually itself. Right? Now, when you open the door, the reed type of a switch is going to open. When the magnet is closed in a close proximity, it's going to close that switch. All right. Now, in this case, we want the pair to be untwisted, just as straight as possible. The reason is that, remember when I told you that the twist acts as an inductor, and inductors hate change, they oppose change. They are going to give you the change, but not as fast as you would like them to, right? So what happens if you open and close the door very fast? There might be not enough speed in this, or maybe it's going to be, actually, it's going to happen too quickly for that sort of inductive wire to pass the signal through. It's going to oppose that change. So this zone circuit on the receiving end might never see the action. So when it comes to this type of applications, yes, we want this thing to be untwisted. All right. You're getting some big dose of a red pill today, guys. All right, but now we're talking about the data transmissions. Right? Keep going. Now, as opposed to unshielded twisted pair, UTP, and it's an acronym that you're going to hear a lot when it comes to telecommunications or data wiring. Right? Also, you're going to hear something or see the thing that is called a STP, which stands for shielded twisted pair. Now, for the most part, we are just a regular residential, or most of the time commercial data wiring. We're going to use UTP, unshielded twisted pair, because we don't need the shield, because there's not enough interference from outside to actually mess with our signal. However, sometimes when it comes to industrial wiring. Let's say you're going to connect different PLC modules or process control, otherwise process control modules that are mounted on machines. Machines have electric motors and whatnot, and all kinds of relays and contacts. There's all kinds of things happening around machines. So that interference produced by the machinery can actually interfere with the data transmissions, data transmission. So in this case, you need not only a not only a twisted pair, but also we're going to provide a little bit of an outside screening or protecting electromagnetic protection, so it doesn't go through through the shield. So it's just an idea of you might want to research that, like a Faraday's cage, right? To basically, because if you have a metal surface, the electromagnetic waves do not go through metal, right? So it's like a shielding screening, so shielded twisted pair, and it looks basically like this, right? Now there are different types of shielded twisted pair cables. Now let's just say what I wrote here about a year ago or so. Although UTP cable is the least expensive cable, it might be susceptible to radio and electrical frequency interference. It should not be too close to electronic motors, fluorescent lights, etc. Yes, a very good point that I made. Give myself a pat in the back. Whenever you are installing data cabling and you're going to run a lot of cables through the ceiling space and otherwise space that is occupied by other things. And the other things could be alarm systems, security alarms, fire alarms. There could be some HVAC systems, heating and cooling, and all kinds of devices, or audio lines, or even power sources. Fluorescent lights are bad. Okay, try to stay away from that, at least 1 foot from anything that basically turns on. Right? Everything that is active electrically or electronically. So that's the kind of a general rule. In fact, in some of the contracts, even when you receive the contracts, it's actually going to be specified that when you're running those wires, keep clear 12 inches or 1 foot, at least 1 foot, from anything that can produce electromagnetic interference. The worst things are thermostats. They are huge noise producers. Security alarms and fire alarms are next, and then there's the HVAC control systems as well, and fluorescent lights. They can actually kill your transmission. Right? Now, when it comes to unshielded twisted pair, when you have a lot of interference, sometimes you have no choice but to spend more money and install shielded twisted pair. Now, the shielded twisted pair cable is available in different configurations. I just listed three ones. Okay, it should be 1, 2, and 3. Right, 1, 1, 1. Well, it's 3, right? Okay, so let's say scenario number 1. All right, each pair of wires is individually shielded with a foil, just like here. Each pair has its own shielding. And over here is something that's called a drain wire or a ground wire, and that actually has to be connected to a ground. Okay. If you have a twisted pair that's a shielded twisted pair that's not properly terminated, sometimes it can be even worse than having a non-shielded twisted pair. Right. So the termination has to be precisely done as per instructions. Right, so that's one scenario. The other scenario would be if there is a foil or braid shield inside the jacket covering all the wires as a group. So there would be no individual shielding, but the main cable would just be having just one common shield. And sometimes you get the double whammy here, which would be there's a shield around each individual pair and there is one more common shield. So that's highly places with high interference, and depending on the environment and the situation, sometimes you have to use one or the other. And of course, the shielded twisted pair is more expensive and more time consuming to install than the unshielded twisted pair. All right. Now, a little bit of terminology, I'm going to tell you that CCA, right? And that is kind of like a pre-word to the next couple of slides that we're going to take a look at, right? Now, copper-clad aluminum, right? So it's copper-clad aluminum. Cladding is basically like a surrounding. So it's aluminum that is surrounded by copper, right? And if you magnify those conductors, this is a huge magnification. It looks like this, right? So there's aluminum wire, and it's just basically coated with copper. The reason for doing that is money, right? This type of wire, because copper is more expensive than aluminum. So in order to save on copper, some companies try to trick the wires to the signal to think that it's using a copper. So these are not as good transmitters or as good mediums for transmitting signal. They are less expensive, but they do not convey the data as good or as well as the pure copper. So some of the cables or some of the conductors or some of the cables that you buy, they're going to be saying that you have to make sure that whether you want a pure copper wires that are inside, or do you want the CCA. Right? CCA are less expensive. My personal opinion is, if you have a choice, try to get the pure copper instead of the CCA. The CCA, sometimes you're asking for trouble. All right, now this table here, you are going to, you know what, you want to copy this table. You want to keep that. You want to, as of all those things that I'm showing you, they're equally important as this one. But this is the one that you might want to copy and keep it somewhere that you can use it as a reference. All right. Now I'm just going to switch from the PowerPoint into the we call it the PDF file, because it's just easier for me to zoom. All right, now we're just going to take a look at some of those cables here. Now, there are different categories. See, there's a Cat XX, so it's a category. So is there a type of cables on here? Now, there's American wiring gauge. So this is how thick those wires are, and the way we look at the AWG, or the gauge of the wiring, American wiring gauge, the higher the number, the thinner the cable is, or the conductor. No cable, conductor. All right. So when the gauge goes down in numbers, that means if the number is lower, the conductor is thicker. All right. Nothing to do with the twist. It's just the thickness of the cable. Twist is another thing. All right. So let's take a look at Cat 5, which is pretty much obsolete right now. You can still use it for basic telephone transmissions, but just for POTS. Excuse me, because even when you try to install the VoIP telephone sets, then Cat 5 is not enough. You have to have more minimum of Cat 5e. The E stands for extended, right? So Cat 5e. Now, Cat 5, you're going to still, so we have something to compare to, all right? So the conductors are the 24 gauge in that. And there is that, the twist is basically, well, it's an arbitrary reference, just to show the comparison between the twists of different cables, right? Now, the pairs are twisted, right? Now, transfer speed, you can transfer 100 megabits per second, right? Notice I'm saying bits, I'm not saying bytes, right? Just remember once and for all, right? We're talking about digital transmission, speed of the digital transmission. We're talking about bits per second. When we are talking about your hard drive storage or your jump drive storage or generally data storage, then we're talking about bytes. And then, of course, we're not talking per second because it's a storage, right? So when it comes to data transmission, we're talking bits per second. When it comes to storage, we're talking bytes. So, so the transfer speed for data is 100 megabits per second for Cat5, right? Maximum length of the link, end-to-end link. So the longest cable that you can use in Cat5 would be 300 feet, right? And then there's something that's called a bandwidth. Now, in this case, the bandwidth is the same as transfer speed. Transfer speed is how fast you can transmit the ones and zeros pulses through the transmission line, and the signal will be understood. The pulses are going to be recognizable at the other end by whatever receives that. And the bandwidth is when you're talking about the analog transmission, right? So like radio waves, for example. All right, so analog transmission, it describes the frequency of, well, let's say, carrier signal that can be injected into this transmission line and transmitted over that transmission line and still be understood on the other end. Now, applications. I just said it's obsolete, not used anymore. I just want you to know that still, when you're going to walk into some service calls, you're going to still see some of the old Cat5 cables being in use. Now the networks are not as fast, right? But sometimes you don't need a fast network, depending on the whatever you're going to use, right? Cat5e, right? Still 24 gauge. You can notice that there's a tighter twist. Now look at that. Here is the transfer speed, 1 gigabit per second, maximum length 300 feet. Here's a bandwidth. Now, that's where things are different here. For the bandwidth, it can carry an analog signal with the frequency of 100 megahertz if it's a CCA, copper cladded aluminum, or if you can transfer 350 megahertz if it's a bare copper cable. The uses: home, small offices, commercial use for data transmission, for network cabling. Okay. Now here we're going to move to Cat6, category 6 cables. Now you see we're using thicker conductors because the gauge goes down from 24 to 23. The twist is tighter. And here's the transfer speed. We're talking about 1 gigabit or 10 gigabits per second, depending on how long the wire is. Right? 1 gigabit per second, 300 feet, up to 300 feet. All right. Now, out of Cat6, you can get 10 times more, 10 times fast transmissions, 10 gigabits per second. However, there's a condition, providing that the link is no longer than 180 feet. So sometimes somebody might want to use Cat6 cable because it's better. Yes, it's better, all right? But if somebody has longer runs, like 200, 250 feet, and it doesn't take much to run that long of a cable, right? Then it just doesn't make sense to pay that much more money if those runs are longer than 180 feet because you're running basically Cat5e specifications, right? So that's why I just want you to keep that table here, right? Now a maximum length, yeah, okay, so for that speed here, and then here's the bandwidth, and it's mostly for commercial. However, more and more often I can see that people want to have that in their homes as well, right? Cat6a, it's just like Cat5e extended. I forgot what the A stands for, but it's basically another fancy word for extended, right? So it's, Cat6a is better than Cat6. Now actually let's come back to the Cat6 first. In Cat5e, the pairs are twisted and they are pushed into a one jacketing, and they are just there, right? They have different twists, but they're there. Cat6, not only the pairs are twisted, but they have a separator, like a plastic separator going along the way, just like a crisscross kind of a thing like that. And each pair has its own channel, a physical channel in that separator, like that. And that separator is also twisted as it go along, right? So it's just like a twist upon a twist. And that's why we can carry things that are faster. Now look, now Cat6a, you can get 10 gigabits, but all up to 300 feet. And here is the bandwidth, 500 megahertz, mostly commercial Cat6a. Then there's Cat7, you can have 10 gigabits and up to 300 feet, and you have 600 megahertz bandwidth. Now, why is bandwidth important? Well, sometimes you want to transmit a digital signal, sometimes you want to transmit analog signal. It depends. Just so you know, the network, the Ethernet part of the network, which is the network wiring inside the building, the LAN wiring, it carries a digital signal through those, the signal is digital, that carries through the wires, through the cables. Now, when it comes to internet signal from outside, that signal is in the analog form. Then you have, the Cat7, Cat7a, Cat8. Of course, the Cat6, as you step up the category, the actual cable gets thicker. So Cat6a is basically pretty much as thick as the coaxial cable, and we will play with those wires when we're in the lab. I'll show you the example. We'll show you the examples of that, right? Pretty much when you go to Cat7, Cat7a, you might want to kind of debate. Well, for the price and for the speed that you need, you might as well go fiber optics. But still, those things are being used. All right. Now, T568 detail. Okay, you know what? We're going to stop right here because we have a few slides to cover, and I don't want to speed through that, because this information I'm going to give you is actually important. Everything is important, but sometimes I put a little bit more emphasis on some information than other. So we're going to continue that. We're going to finish this, the rest of this presentation next time we see each other, a week from now, and that's going to be, that's that. All right. Okay, so you have about 10 minutes to get to your next class. Are there any questions when it comes to anything that we have to do with our course? You may type it in the chat line, or you can, if you wish, you can pipe in just with the voice. That's fine. If not, we're going to wrap up for today, and I'm going to see you a week from now, and some of you are going to see maybe next week. Who knows, right? Cool. All right. Have a good day, guys. Thank you very much.